If you haven't already tried this example problem, go ahead and try it yourself. Hopefully you've tried this example problem, and now we'll go through it. We're told that water is draining from a conical tank at the rate of 2 meters cubed per second. So that means that the volume, dV dt, is changing at 2 meters cubed per second, and I know it's a volume because of the units. The tank is 16 meters high. That's the most amount of water that could be in there. And the radius of the tank is 4 meters. We'd like to find dH dt. We want to find it when the water level is 12 meters and when the water level is 2 meters. So some things to notice about this situation. We have a cone, and at the beginning the radius of our circle is 4, and this happens when the height is 16. So that means that proportionally, the way the radius relates to the height is a 4/16 relationship, or a 1/4 relationship. And if we were to just consider this proportion, this means that 4r equals h, or that r equals 1/4 h. And this relationship is going to prove to be important and valuable for this kind of problem, that the radius and the height have a relationship to one another, that the radius is always 1/4 the height, no matter where the water level would be in this cone. So that's kind of the catch on this kind of a problem. Now for question A, we want to know when the height of the water is 12 meters. And when the height is 12 meters, that does mean that the radius, since it's 1/4 of the height, will be 3 meters. And since we have a cone, we know that the volume of our cone, which is the same shape the water will be in at all points, is 1/3 pi r squared h. And we want to know exactly when the water is 12 meters high, and this is exactly when the radius is 3. We can also get this entire thing in terms of h, because we know that r is 1/4 h. So by substitution, this will become 1/3 pi times 1/4 h squared times h. Taking this a little further, this means that, because this will be 16 times 3, which is 48, so we've got 1/48 pi h cubed. Right? So that's the volume of water in terms of just the height. And so when we take the derivative, this means that dV dt will equal, when I bring the power down, that'll be 3/48, which will simplify down to 1/16 pi h squared times what we want to know, dH dt. Now in part A, we know that dV dt is 2. That'll equal 1/16 pi. H in this particular case is 12, so this will be times 144 times what we want to know, dH dt. If I multiply both sides by 16, I'll get 32. That'll be divided by 144 pi. And simplifying this just a bit, this fraction comes down to 2 over 9 pi. And since it's a change in height, this will be meters per second. And that's what dH and dt equals when the height of the water is 12. Now in part B, we want to know what is it when the height of the water is 2. So again, all our work is the same to this point, but what changes is the height is 2. So this means by substitution that 2 equals 1/16 pi times 4, because that's what 2 squared is, times dH dt. And when I multiply both sides by 16, I'll get 8. Divided by 4, I'll get 2. So this will be 2 over pi. And this again will be meters per second, is what dH dt equals in this case. There you have it.